Hello everyone, we are Group 60 and this is our research methodology presentation. This paper was presented at 45th IEEE Symposium on Security and Privacy 2024. The paper titled Sherpa Explainable Robust Algorithms for Privacy Perceived Federated Learning in Future Networks to Defend Against Data Poisoning Attacks. This paper has 4 authors including Chamara Sandeepa, Bartolom Simowski, Shen Won and Madhushankar Liyanage from University College Dublin. Moving to the next slide, to give a brief background about the work, the focus on federated learning, which is a distributed machine learning technique that allows model sharing and aggregation. In the figure to the right, we can see a cloud service provider together with the multiple clients. So many clients can contribute into the federated learning process by forwarding their local models into the service provider, which aggregates these models together and return these models back to these clients. Unfortunately, these can be malicious clients who can send poison model updates to the poison model, can be crafted by injecting malicious data into the model training process such that these local models can train by these malicious factors will be poisoned, and these poison models can lead to degradation of the aggregation in the final model, which affects the overall accuracy of the final step. Moving to the next slide. So therefore, their motivation lies on the limitations of current solution, such as the model similarity matrix and also arbitrary threshold cutoffs to detect and filter these poison models. So typically, the model similarity matrix, like cosine similarity or set of threshold cutoffs, may limit the capability of the overall model convergence, as well as they do not provide clear explanation on how specifically the poisonous behave related to benign clients, and also what key features distinguish these poisoners from the benign clients. Therefore, the contributions include the novel algorithm Sherpa, which is an explainable, robust algorithm for detecting and eliminating the poisoners. For that, they use SHAP-based feature attributions to detect important feature differences in a poisoning client. They also demonstrate how poisoning can impact on the client privacy and the mitigation of the privacy threat from poisoning. So if we take a close look at the poisoning attack on a federated learning, these attacks can aim to alter decision boundary of the model, degrade the model performance, as well as to introduce backdoors. So these backdoors can be a part of another attack like property or membership inference attack. So often related literature use these poisoning attacks as a mean to launch other privacy-related attacks like the membership or property. So next, Oshan will discuss about poisoning attack detection via SHAP.
Okay, so now let's discuss about the poisoning attack detection via SHAP-based feature attributions. To address the poisoning attack detection in federated learning, authors of this paper has developed a poisoning detection technique using SHAP-based feature attributions. This method identifies differences in feature importance between benign and poisoning clients. As illustrated in the below figure, benign clients typically display red regions in Sherpa visualization, indicating high feature importance, while poison clients show blue region, significantly low feature importance. This distinction enables an aggregator to inspect clients using SHAP technique. The aggregator maintains a small representative data set to generate these SHAP values, facilitating the detection process. Now, move to the next slide. Within the federated learning framework, a virtual aggregator connects multiple clients and employs a robust aggregation algorithm to analyze client models. By leveraging SHAP, authors have extracted feature attributions and clustered them to identify poison clients. Hyperparameter tuning is incorporated to enhance the overall accuracy of this process as well. And clustering these feature attributes allow us to detect poisonous using various techniques, including visualizations of client feature attributes, ultimately enabling the elimination of detected poison clients. Now let's move on to the next slide. The poison detection process involves several steps. Feature attributions are derived and flattened into vectors, as shown in Figure A, where poisoned attributes deviate from benign ones. These vectors are processed through the HDB scan clustering algorithm to calculate mutual reachability distance, which forms multiple clusters for each class in SHAP values. As depicted in the figure C, two clusters, cluster A and cluster B, emerges with poisoned feature attributes falling under cluster B. Each client's SHAP-based attribute for class C belongs to desired cluster QC. If a client's attribution deviates from its cluster QC, it is flagged as suspicious. Clients with feature attributes exceeding the average suspicious count are eliminated as poisonous. And moving to the next slide. Now let's see how poisoning visualization works. To visualize the poisoning situation, authors of this paper where poison clients are clearly identified with a red. These poison feature attributes deviate from their original cluster positions, forming an anomalous cluster. When examining SHAP-based feature attributes, benign clients such as client number 3 exhibits higher accuracy and feature importance. In contrast, random poisoning scenarios lack clear patterns in accuracy and attributions compared to benign clients. In targeted poisoning, the targeted classes may show accuracy, but other classes lack the consistent trend observed in the benign clients. Now, Chanmini will discuss about the evaluation of SHAP method.
Now let's see the evaluation of Sherpa. To evaluate the algorithm, the authors have used different types of poisoning, which is continuous and periodic poisoning. In that, we can see the continuous poisoning has a higher impact on accuracy compared to the periodic poisoning. But for both cases, their defense mechanism can detect these poison updates and eliminate these poison updates from the process, such that the accuracy will remain similar for both cases. And also, the main task accuracy of the algorithm does not harm the overall accuracy even if the system runs without poisoners. For example, if we see the table shown at the top, we can see the federated learning accuracy remains the same when the system is implemented with the defense. But if we don't actually implement any defense, we can see a clear degradation of the overall accuracy. And also, the federated learning defense accuracy is higher across different types of datasets. As we can see from the bottom table, we can see the defense accuracy is high for all the types of datasets, including the true positives, true negative, false positive, and false negative rates. Then they also compare the algorithm with the existing benchmark techniques like Fool's Gold, Mott, and Crumb. For this case, they have evaluated 20 clients running 10 global iterations, and they have considered 2, 6, 10, and 16 poisoners out of these 20 clients, which accounts to 10%, 30%, 50%, and 80% of poisoning situation. Despite the level of poisoning, the algorithm is able to correctly detect the poisoners even if the poisoning amount is significantly high, like 80%. Over to you, Ashen.
So let's talk about poisoning-based privacy attacks and defenses. So in this paper, they have also evaluated their system against privacy attacks by using targeted feature poisoning. So this technique helps to enhance property inference attacks. For example, if we look at this figure, we can see a series of spikes when poisoning is applied. So these spikes happen at each stage where property inference attack takes place. In this case, the attack was launched on Celeb A dataset by targeting the property hair color. With poisoning, there is a sharp drop in the federated learning accuracy. So this decline indicates that the targeted hair color property is appearing in the system. The attacker can use this to drop to identify when the property appears during the learning process. And however, when a defense mechanism is applied, this inference attack fails because there is no noticeable decline in accuracy. And comparing the system with and without poisoning, we can see that both the poisoning accuracy and property inference accuracy decrease, like from 85% down to around 31%. And next we see what are the factors affecting to clustering. And so in this paper, they have also looked at the different explainer types for SHAP, such as like deep explainer and gradient explainer. So both of these explainers show similar accuracy in detecting poisoning, and increasing the amount of representative data used to calculate SHAP values improves accuracy, but also increase computation time significantly. And for example, using 1 unit of representative data took about 0.5 seconds, but if they increase it to 10 units, time over the 5,000 seconds. So that's showing a clear trade-off between accuracy and speed. Next, we talk about their conclusion and what are the future works. So their work explored using feature variations in SHAP as a defense against data poisoning in federated learning. And the SHAP techniques provide better model explainability and helps to justify removing suspicious client updates. So the approach achieves a higher detection rate than existing robust algorithm. And in terms of future works, they plan to make the federated learning system more lightweight for detection and improve compensation for minority feature contributions. So that's all about our presentation, and thank you.